I want to start the second part with this problem that I stopped at the end of the last part. And the reason I want to start with this is to show you that this part C, regrettably, cannot be done without more information than was given in the problem. If you look, in order to do this, you have to know not only the angle involved, but also the wavelength and the distance between the two slits. And unfortunately, I didn't give you either one of those. And there's no way from this previous information that we can calculate that. And so this, in order to do this part C, you have to know both of those actually. Now, moving back to what we're doing here, let's move on to something called multiple slit diffraction. Multiple slit diffraction is just what it sounds like. Basically, instead of two slits, we have several slits that are side by side, and what you can see here is that you end up forming first and second order rainbows, and the rainbows occur because of the various wavelengths that come through. So you start out with what's known as a diffraction grating. A diffraction grating is a grating that has a large number of slits that are evenly spaced with equal distances d between each slit. And so with each of these in a two, when you look at two together, you end up with the same formula, d sine theta is equal m lambda for m orders 0, 1, 2, and 3. But a diffraction grating, because it has multiple parallel slits, has a different outcome. When light passes through, it's diffracted in a very similar manner to double slit with various light and dark regions, but the pattern that's obtained starts with white light, and you end up with the central white maximum, but the higher order maxima disperse the white light, and the various levels of constructive and destructive interference results in a more rainbow effect. And this diagram shows exactly what happens. A diffraction grating shows the light rays from each slit traveling in the same direction. Each ray travels a different distance to reach a common point on the screen. So if you can imagine the previous diagram where we showed the two slits, you can see that there's a delta L for each for a common point. Each ray travels a distance of d sine theta different from its neighbor. So the sine theta is different from its neighbor. The diffraction gradient considered in this example produces a rainbow of colors on the screen at a distance. X equals 2 meters from the grating. So we assume a distance from the grating of 2 meters. And by doing that, you can calculate based on theta and y, what y is. The distance along the screens are measured perpendicular to the x direction. In other words, the rainbow pattern extends out from the page, out of the page. Calculate the wavelength of light that has a second order maximum of 45 degrees when falling on a diffraction grating that has 5,000 lines per centimeter. In order to do this first problem, what we need to do is look at our equation that we've used before. D sine theta is equal to m lambda for m's 0, 1, 2. The question here is to calculate the wavelength, so we want to solve this equation for lambda. And lambda is going to equal d sine theta divided by m, and d is going to be, you have 5,000 lines per centimeter, so you have 1 centimeter divided by 5,000 or 1 times 10 to the minus 2 meters divided by 5,000, and that's going to be 2 times 10 to the minus 6 meters. So 2 times 10 to the minus 6 and times the sine of 45 degrees, which is 0.707, divided by, and it's the second order, so that's 2. Lambda ends up being 7.07 times 10 to the minus 7 meters. And you can change that to other units if you want to. Now, the second problem states that asks what's the spacing between the grating and a feather that acts as a reflective grating, given they produce a first order maximum of for a 525 nanometer light wavelength at 30 degrees. Use the same problem, but now we're going to solve this problem for D. D is equal to m lambda over sine theta. M is 1, first order gradient. 525 nanometers is 525 times 10 to the minus 9, or 5.25 times 10 to the minus 7 meters, divided by the sine of 30 degrees. The sine of 30 degrees is actually 0.5. And you do that math, and you get 1.05 times 10 to the minus 6 meters. And again, you can convert that to another unit if you want to. Now let's look at the next thing, which is single slit diffraction. A single slit diffraction pattern is when monochromatic means a single wavelength, passes through a single slit, and it has a central maximum, as shown here, and many smaller and dimmer maxima on either side. The central maximum is 6 times as intense or as high as the other maxima. The drawing shows that the bright central maximum and the dimmer and thinner maxima are on either side. Light passing through a single slit is diffracted in all directions and may interfere constructively or destructively depending on the angle. The difference in the path length for the rays from either side of the slit is seen to be d sine theta. And you can see here, d again is this slit width, and when it passes through, there is again this change in path, and it's shown right up here. The change in path again is d sine theta. So, if you were going to look at this, the graph of a single slit diffraction intensity shows that the central maximum is wider and more intense, as we said before, and the central maximum, again, is 6 times that expectation. But what this also shows is that this minimum is equal to the wavelength divided by the slit. Then the next minimum is 2 times the wavelength divided by that. This next minimum is 3 times, etc. So d sine theta now applies for destructive as opposed to constructive. So all of these, what I just said, was in terms of the sine of theta. So this is lambda over d sine theta. This is 2 lambda over d sine theta. This is 3 lambda over d sine theta, and so forth. So the same formula is used, but now we see that these are the dark parts instead of the light parts. A graph of single slit diffraction pattern is analyzed in this sample. And so what we have here, you're passing through D, here's lambda here, so the central maximum is here, the first theta is here, and it's going to be lambda over d sine theta. Then the second one is 45 degrees, so this is lambda over d sine 45 degrees, etc. Find the wavelength of light that has its third minimum at an angle of 46.8 or 48.6 when it falls on a single slit width of 3 micrometers. So in order to do this first problem, again, you use the same equation, but now we're looking at minimums instead of maxima. It says find the wavelength of light that has its third order at 48.6 when it falls on a single slit width of 3 millimeters. Okay, so we have d sine theta is equal to m lambda, and it's find the wavelength, so we're going to solve this equation for lambda. So that's going to be d sine theta over m, and m is 3, d is 3 times 10 to the minus 6, m is 3, and sine of 48.6 and if you do the math here, lambda ends up equal 7.50 times 10 to the minus 7 meters, which is 750 nanometers. The second problem, these are actually both together. I'm not sure how my typing got that way, but you'd use the same formula here. You got a sodium vapor light that's averaging 589 nanometers in wavelength. It falls on a single slit, and it wants to know the angle to produce the second order minimum. So again, use this same thing, but now you're going to solve for the sine of theta. So this is the second order, so this is 2 times 5.89 times 10 to the minus 7 divided by 7.50 times 10 to the minus 6. And if you do that, you get 0.157, and that's the sine of this angle, so theta is equal to 9.03 degrees. What is the highest order minimum produced? This time I gave you enough information to calculate that, and you want to know m, and m, going back up here, m is equal to d sine theta over lambda. And so we know that lambda is 5.89 times 10 to the minus 7. D is 7.5 times 10 to the minus 6. So what do we put for sine of theta? Well, theta, the maximum here is 90 degrees. So the sine is 1. So when you want to know the maximum, you assume the angle of 90 degrees. It can't be greater than that. And if you do the math here, you get 12.7, or you use round numbers here and always round down. So